So now that we've picked out the proto board to put the ROM card on, I sat down and drew up a schematic, as you can see by hand here, exactly as I would have done if I was designing this, 40 years ago. Let's talk through the schematic a bit and why I believe this will work. So what you'll see here on the schematic, these outer numbers out here are the pins on the 100-pin edge connector. This pin happens to be A15. A15 through A11 are sitting here. And so what the circuit does basically is this, is we have an 8-input NAND gate. And basically what happens here, if all the inputs are ones, the output will go low. So I've taken these three extra outputs and just tied them to ones. I've tied A15 to A11 to it, and what will happen here is when all 5 of these address pins are high, this output will become low. That does a couple of things. Next we have down here A10, A9, and A8, and those get used as bank selects to select one of 8 256 byte banks. If the output here is high, coming into D, it can only select 8 or 9 here as the outputs. This is a 4-to-1 demultiplexer. So whatever the binary combination is on these 4 pins, it'll take one of these outputs low. So with D being high, that's equal to 8. Or I got to make sure I'm thinking about this right. Yeah, that's 8 or higher, which says these outputs will become basically active. So this guy low, basically the chip is enabled to pick one of the 8 outputs down here. And then depending on the state of A10, A9, and A8, it'll take one of these output pins low. If they're all zeros, it'll enable ROM 0. If we have a 1 here on A8, this pin will come low and it would have picked ROM 1, ROM 2, ROM 3, all the way up to, they're all 3 ones to ROM 7. So this is used to say we're in the upper 2K of memory, and in that space, which of the 256 byte EPROMs do we want to enable? There'll actually be 8 EPROMs here on the board. I've only drawn 2 in the board here. There's actually 8 that'll go across here. Each one of these enable will come out to one of the individual ROM chip enables. It's an active low chip enable. So if ROM 0 is being accessed, it'll take chip enable low. And what that'll do from ROM 0 then is say, depending on the address that's coming into me on A0 to A7, it's data pins, and I've represented the data pins on this side of the schematic over here, would output the data for that byte. And then with output enable low here, this OR gate here will become low when SMR, which is memory read, goes high. So this is pin 47 on the bus, memory read. So memory read goes high, gets inverted to a low. The 2 lows give me a low. That enables these 1897s to output the data on the input side onto the data in on the bus for the 8080 to read. So really, this should work. This is really all we need here to decode the addresses and get the EPROMs on the bus. The bit of the schematic you see up here has to do with generating wait states. Because these ROMs are pretty slow, they're like 1 microsecond access time, we need to inject wait states to allow the ROM time to actually catch up and get its data out. And that's what this little set of flip-flop circuits up here does, is we have the 2-phase clock for the 8080 that are being fed in here. And P-Sync. And basically what's happening here is that this is creating basically a delay based on the clocks. And what happens here is when output enable goes low here, this 1897 is enabled and the output of Q0 is passed to the P-ready pin on the bus. And basically Q0 will go high, it'll hold the machine for 2 cycles, and then release it. The machine will read the data that's now stabilized and process it. So that really is the entire schematic. So a couple of the design considerations I had here were this, is I only wanted 1 TTL input on the XOS 100 bus. And that's the reason I have these buffers sitting here. So the A7 to A0 come in and they're buffered, and then the A0 output of the buffer is going to go to all 8 of the EPROMs. It's not drawn that way, but it'll go to pin 3 on all 8 of the EPROMs. And that way the bus only sees 1 TTL load, the 1 input, and then the driver takes care of driving all 8. I'm doing that to respect the bus. Let's put less load on the bus, really becomes the driver's chip here's function to actually drive the 8 inputs. There's a thing with TTL logic called fan out, and that is how many inputs the output of something can actually drive low. And because there's other cards in the bus, I want to respect that. So we really only have one TTL load on these pins. We only have one on these pins, one on these pins, and one on these pins here on the board as well, along with SMR. So really, that's it. I think I got a pretty good shot of this working as is. I plucked pieces out of other designs. There's some extra gates involved here. So there's 7 extra buffers. It's just kind of how it worked out. 3 extra OR gates and 4 extra NOT gates or inverters. And with these 4 extra inverters, you could actually go up here and inject an inverter if you wanted to on one of these pins to move the block of memory, down 2K. I've just got it hardwired here because this card's designed to be in the upper address space of the machine from F800 to FFFF. We'll find out once we wire wrap this if the schematic works. The next thing I always do is collect pinouts. And these are the pinouts of the various devices I'm going to be using. We've, of course, got the 1702 EPROM, and it's an interesting part. And we'll talk about this. You'll notice there's no ground pin on here. There's no VSS pin. There's -9 and +5. And that's the only supply rails it has. And because it's kind of unique power-wise, I went ahead and added power pins on here. So +5 goes to all 5 of those pins, and the -9 to these 2. You'll notice on the other devices I haven't indicated power. Didn't really need to. But this gives me basically, the pinouts for all the devices. This then moved on to where I'm going to put the chips on the board. So this is looking down at the S100 card. We've got our 8 1702 EPROMs. It's going to be, at the F800 address, the F9, the FA, etc. And each one of the chips is here: the LS30, the LS04, the 7442 that does the 3 of 8 decoding, the buffers for the buffs. So this gives me a layout for the proto board, and I always use it to indicate power. So in this case, I've got -9 volts going to pin 24 on each one of the ROMs, and -9 going to 1314 pin 16. And if we go back, we'll see -9 to 24 and 16. We'll also see the power pins in the TTL devices. So VCC is usually up in this corner. Pin 1's indicated by the dot. And ground is usually down in this corner, so those are all marked. And if we look at the 7430 here, we'll see there's 3 pins I actually have tied to +5 to force those to always be 1s. And those are indicated here by the pluses here as well. So this gives me a power map. We kind of have the same thing over here on this device, on this 1897 device F. You'll see pin 15 and 1 are being held low. And we'll find this here, pin 15 and 1 on device F are being held low, and pin 15 on G. And on G, I've got pin 15 being held low. So it basically gives me a power map, so I don't have to drive another board, and then I can come in here with like a voltmeter on the actual board and just probe these out to make sure that they're at the levels I expect them to be. This then moved us on to the card that we looked at earlier, and where I am in the construction of the card. So I've got the chips laid out on the board as we saw. So notice that these 6 sockets down here aren't used to hold chips. The pins in these sockets poke through the board, and these pins are connected to the fingers on the edge connector, and that's how I'll wire up onto those pins to bring the signals up into the card. So we've got our 8T97 sitting here. We've got our 17 EPROMs will sit up here, and we've got that logic we looked at in the rest of the circuit. There's a view from the top of the card. You can see I've got the 7805 regulator in here. +8 is being brought in, hitting a bulk capacitor. +8 comes up to the input on the regulator. Middle pin is ground. The output of the regulator comes off and goes off to a bus on the board. And every place I have a red mark here indicates that that piece has got +5 on it. The thick coppers here are all ground. The thin ones are all +5 with the exception of this bus down here, which isn't hooked to anything. This is a little hard to see on the back of the card, but there's where those wire wrap pins for those 6 sockets we saw on the bottom of the card come up through, and you can see they're numbered. 2 through 9, 10 through 11. Is it really 17? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So yeah, 17. Except that they're all numbered, and I'll be wrapping onto these posts to pick up the signal and bring up to the card. Now, this is kind of hard to see. You can see some of the wire wrap pins kind of standing out along here and here. But what I've done here on this card is I've actually taken the pins that go to the ground or the power bus, and I've just bent the wrap pin over and soldered it on. So if you remember looking at the 72 EPROMs up here, let's go back here to the power map. On the 1702 EPROMs, we've got pin 23 and 22 to +5, and 13 and 15, and 12. And you can somewhat see it here. So we've got pin, got to read this correctly. So we've got pin 12. Looks like it's down to, that doesn't seem correct. Have I got a mistake here on the board? That would be a plus power bus. Oh yeah, it goes to +5. So pin 12 goes to +5. It's been over and soldered here. There's pin 13, 14, and 15 come to this +5 bus. And then 23, or is it 24? Anyhow, you can see I've got the pins bent over here on the devices. We get down to these TTL devices. You'll see that for this TTL device right here, I've got pin 7 going down to ground, the wide bus, and I've got pin 14 coming over here to +5. So what I've done is taken the power pins on all the devices, and I've just bent the pins over and soldered them directly to the bus. And then I will use wire wrap for everything else. So in the case of, let's go back all the way back to the beginning, these extra pins right here that go to, are tied to +5 in the schematic. So that 7430 is the device out here on the end, which will become the device out here on this end. It'll be this chip right here. I will wire wrap those pins and then solder the wire wrap to the +5 rail. That way, I don't want to bend the pins over. That way I can remove that wire wrap if I decide to reconfigure the card, or if I need to use those inputs for like some other address decoding scheme. So only really the power pins are bent over and captured here. Is this the best technique? I really can't say. I've still got to work the -9 volt regulator into here. I've got a LM7908 on order. That's a -8 volt regulator. And we'll be adding a couple of resistors to push its ground pin basically up a volt to get it to -9, or actually I should say down a volt. So really, there's where we are. In the previous video, we kind of stripped this card down, did some cleanup. This is really where I've got to. So I think it's going to be a pretty sharp-looking card. I've got plenty of room left out here. If I need to add additional chips, say my decoding scheme doesn't work correctly and I need to add another chip to do something else, there's plenty of room to do that. There's plenty of room here if I need to add an extra 1897 buffer or 2 or 3 here. Lots of room on the card. I've got some 0.1 microfarad disc to spiking caps kind of on the power rails here, the +5 distribution. I'll probably add a few in circuit, although the clock speed of this is low enough they probably won't be needed. There's some bulk capacitance here on the 5 volt output. I probably need to add a small electrolytic from the input to ground here as well. Just really haven't done it yet. But there it is. I guess the final thing I'll talk about quick in this video is as I start to wire wrap this, I will wire wrap really these 2 chips first, A and B. Then I'll be able to put the card in the machine, and from the front panel I'll be able to basically read address F800. And if this is working, I'll see this pin pulse low when I do that read, and I'll see this pin pulse low. And then I can go to address F900 and do reads, and I should see this pin pulse low, also with that one. And so I can debug that section before the rest of the logic is on here. And once I'm convinced those are working correctly, I will most likely add really the wait state generator here. And every time I do a read, I should see, again, a pulse appear here on Q, where it'll go high, put the machine in P ready for 2 clock cycles, then drop low, and the machine can continue running. So probably wire that up next. We'll get these 2 pieces in place, and then it'll really be a matter of the huge amount of wire wrapping, which is all 8 of the 1702 sockets. Every pin on the 1702, that wasn't soldered to a power rail was just going to be, wired in bus. Pin 2 to 2 to 2 to 2 to 2, 3 to 3 to 3 to 3 to 3. The only pin that'll be unique is pin 14. Those are the chip enables. So really we have a schematic. We have an approach to wrapping this and testing it in stages. We'll see how it goes. So we'll pick up in a future video with wire wrapping here. I hope you enjoyed kind of the view and or a look into the little view about how I approach these kind of projects. It's been a long time since I've designed an S100 card. I guess I should say here I'm designing this for the Altair bus, not the IEEE 696 bus. So this card wouldn't work, in a later generation S100 machine. I'm really designing everything here around the Altair bus and the original Altair. I keep saying Altair machine. So I'll wrap this up here, and we'll talk soon.